This is a short screencast to explain using dynamic programming to solve the change-making problem. So what is the change-making problem? Given an amount of money, say, you use the smallest number, fewest possible coins from a denominations d1 through dn so that the total value of coins is equal to n. So we're trying to minimize the number of coins that we're going to use. Note, there's a solution for all values of n if and only if the smallest denomination is 1. I mean, that's kind of obvious because if you don't have 1, you can't even make change for 1. For some sets of denominations, in U.S. currency, for example, a greedy algorithm actually solves this problem. Just continue to use the largest coin possible until it doesn't fit, and then use the next largest coin. And this will give you an optimal solution. But there are lots of examples where the greedy algorithm does not find the smallest number of coins. Probably the simplest to think about for us, being Americans, is that in our currency, if we just did away with the nickel, then all of a sudden greedy wouldn't work anymore. If you took, say, for 30 cents, for instance, and you picked the quarter first, 25 cents, then you'd end up with having to use 6 coins. Whereas if you just use 3 dimes, you'd be able to make change for 30 cents with fewer coins. So let's talk about how we would approach this. So as you recall, the important thing, the most important step is the first step, and that is to try to understand what the optimal substructure of the problem is. So for change making, just suppose that you know what the largest denomination used in a solution for k is, and suppose that it's d. Then f of k minus d must be the minimum number of coins used to make k minus the amount k minus d. That's the optimal substructure. And I think that's pretty obvious. If you could make a f of k minus d with a smaller number of coins, then of course you could make the solution for k with a smaller number of coins. So let's look at the recurrence relation here. F of k is the min over j, where dj, that should be less than or equal to k. Then the minimum of f of k minus dj plus 1. So in other words, all you do is you look at all the denominations that will fit, in other words, that are less than or equal to k, and you see once you use one coin, namely a coin of one of those denominations, then how many coins does it take to make change for the remaining amount, which is k minus dj. Okay, and obviously the initial condition is you don't need any coins to make 0. So let's work through this example a little bit. So if we need to make change for 1, then that's pretty obvious. We just need 1 coin. Remember again, the example we're considering is d1 equal to 1, d2 equal to 3, d3 equal to 7. So the denominations are 1, 3, and 7. And we want to solve this problem for n equals 16. So we start here again at 1. That obviously takes 1 coin. 2 takes 2 coins. 3, now we have a denomination of 3, so that only takes 1 coin. 4, now this is sort of the first interesting one. What do we have to do here? We have to try 3, okay, and then 4 minus 3 is 1, so that's 1 plus the 1 coin for the 3-cent denomination, and so that's 2. Or we could try 1, and then that would also be 2. We check 4 minus 1, and that's 3. That only took us 1 coin, so that would be 2. Okay, in a similar fashion, 5 is equal to 3. We try the 3 again, denomination of 3. That brings us back to 2. 2 plus 1 is 3, so that's 3. If we use 1 cent coin, we go back to here. That takes 1 coin for going to get back to here, and then 2 coins to be here. So that's 3, and then 7 won't fit. So again, we get 3 coins for this. 6, okay. 2 3-cent coins will work, and you can see that because if you go back 3, you get to 3, and that only took 1 coin. 7 again won't fit. If you try 1, it'd get you back to 5, and that would be 4. Okay, so 2 is less. The 2 we got from taking the 1 coin for 3 plus another coin for another 3. That 2 is smaller than the 4 that you would have gotten if you'd used the penny denomination. Okay, in a similar fashion, I think you can work through most of these. If we're trying for n equals 16, let's just kind of go through that one a little more carefully. So now 7 will fit. Okay, so we'll start with 7. 7 gets us back to 9. 9 took 3 coins, so that's 3 plus 1 equals 4. So for 7, we need 4 coins. If we use a 3, the 3 takes us back to 13. That also used 3 coins, so 3 plus 1 is another 4. So that's also, so 4 is still the minimum. And then if we try 1, we get back to the 15. That also used 3 coins, so we get 4. So there are 3 solutions, actually, for 16. 3 different, well, not entirely different solutions, but the 3 things that we checked for D1, D2, D3, there's actually, I mean, we get the number 4 that we need 4 coins, no matter which denomination we use to go back. So that's about it. That's just a quick introduction to change making. If you look in your text, there's a little bit longer discussion in a text, and I encourage you to do that before you try the homework problems.